Hello friends, here in this video we will see a problem which is based on Carnot cycle. Here is the question which we have. Now I'll go on reading the question and write the data along with it. Now here it is given that in a Carnot cycle, first of all, since the name of the cycle is known to us, so I'll write down in the type here, the type of cycle is Carnot cycle. Then the maximum pressure and temperature are limited to 18 bar and 410 degrees Celsius. So the maximum pressure is 18 bar and 410 degrees Celsius is the maximum temperature. So I'll write down maximum temperature, maximum pressure as P max, that is 18 bar, or it can be written as 18 into 10 raised to 5 Newton per meter square. Then and the maximum temperature is 410 degrees Celsius. So T suffix max is equal to 410 degrees Celsius. So that will be 410 plus 273. So therefore the maximum temperature will be 683 Kelvin. Next, the ratio of isentropic compression is 6, and to explain this we will need the Carnot cycle PV and TS diagram, that is for the data we need to draw the Carnot cycle on PV and TS diagram. So I'll start with that. Now on the PV and TS diagram, the first process for Carnot cycle is isentropic compression. So compression takes place from 1 to 2, and as we see during the compression process, volume at point 1, volume at point 2. So the volume decreases but there is increase in pressure, that is P1 to P2. Next, the second process in case of Carnot cycle is isothermal, or we can also call it as reversible isothermal heat addition process. So isothermal process is also shown in the form of a curve. So this is the isothermal heat addition process. Next, process 3 to 4 is again like isentropic compression. Now we have isentropic expansion process, and then process 4 to 1 is reversible, or we can say reversible isothermal heat rejection process. So now here, once we have completed the PV diagram, here I am drawing the TS diagram. The first process is isentropic compression, so it will be shown by a vertical line, straight vertical line, process 1 to 2, isentropic compression, wherein the entropy remains constant, that is S1 is equal to S2, and there is increase in temperature from T1 to T2. Next, after isentropic compression, the process is isothermal heat addition. So isothermal means there is constant temperature heat addition from T2 to T3, and then there is again isentropic expansion. Isentropic expansion shown by a vertical straight line, wherein the entropy remains constant, S3 is equal to S4, and there is drop in temperature, that is temperature drops from T3 to T4. So T2 is equal to T3 and T1 is equal to T4. Then process 4 to 1 is isothermal heat rejection process. So here I have shown T1 is equal to T4, the isothermal heat rejection process. Now after this I will show that in process 1 to 2 work is done into the system, that is compression. So it is this arrow is going inside. 2 to 3 is the heat addition process, QA. 3 to 4 is isentropic expansion, or we can say we are getting work output from the system. And 4 to 1 is heat rejection process, that is Q suffix R. Now, once I have completed the PV and TS diagram, I'll read the data again and write it as per this diagram. That is, here I know all the points. So the next thing would be after the maximum pressure and maximum temperature. Now we can understand that in a Carnot cycle, the maximum pressure and temperature are limited to 18 bar and 410 degrees Celsius. So 18 bar is the maximum pressure, and from the PV diagram it is clear that maximum pressure is at 0.2. So this P2 is the maximum pressure. Here I'll write down this P max was nothing but it was P2. And then the maximum temperature is 410 degrees Celsius. That maximum temperature T max is T2 is equal to T3. So T max was, here I can write down T2, and it is also T2 is equal to T3, that is T max. Then after reaching here, the next part of the question is the ratio of isentropic compression is 6. Isentropic compression starts from point 1 and ends at point 2. So V1 by V2, that is called as the compression ratio, and that is given as, I'll write it as R suffix C, that compression ratio is V1 by V2 and it is given as 6. Next, and isothermal expansion is 1.5. See, this isothermal expansion is for the heat addition process, not for isentropic expansion. In the problem it is given that it is isothermal expansion. So expansion takes place from 2 to 3. So it will be final volume, that is volume at 0.3 by initial volume which is at 0.2. So V3 by V2 is the ratio during expansion, and that ratio is given as 1.5, the ratio during isothermal expansion process. And after that there is isentropic expansion. Next, assuming the volume of air at the beginning of isothermal expansion. At the beginning of isothermal expansion starts at 0.2. So at the beginning the volume is 0.18 meter cube, means volume at 0.2. So V2 is equal to 0.18 meter cube. Now the question is determine temperatures and pressures at all salient points. So we have to find out the temperatures, that is T1, T2, T3 and T4 at all points. Similarly pressure P1, P2, P3 and P4 at all salient points. Next, second question is change in entropy during isothermal expansion process. Isothermal expansion process is from 2 to 3. So for 2 to 3 process we have to find out the change in entropy delta S, and at last we have to calculate how much is the Carnot cycle efficiency, that is efficiency of Carnot cycle. So these are the questions which we have to solve. Now if we have understood the data, we can easily start with the solution part. So let us get started. Now in the solution part, the first thing which I am calculating, it is calculation of all temperatures and pressures. That is, we would be calculating the temperatures and pressures at all salient points, or we can say the 4 points which are there in the diagram. Now I'll start with the first process, that is for process 1 to 2. Now as we see here, process 1 to 2 is isentropic compression process. So I'll write down for process 1 to 2, that is reversible adiabatic, also called as isentropic compression process. And for this I have the relation that T2 upon T1, that is final temperature upon initial temperature, is equal to V1 by V2, that is initial volume V1 to the final volume V2, V1 by V2 raised to gamma minus 1. Next, I can say that it is also equal to V1 by V2 is given in the problem. It is nothing but R suffix C. So it is RC raised to gamma minus 1. So therefore T2 upon T1. Now T1, it is not there in the problem. T1 is what we have to calculate. So I'll keep T2 by T1 as it is equal to RC is given, that is 6 raised to gamma minus 1. Gamma is 1.4. I'll write down, assuming gamma is equal to 1.4 for air, because air we can use it as a perfect gas. Now therefore T2 value is given in the problem. T2 is nothing but the maximum temperature, which is 683. So 683 upon T1 is equal to 6 raised to 1.4 minus 1, that is 0.4. Now if I send T1 on to the other side and divide 683 by 6 raised to 0.4, my answer is 333.55 Kelvin, and that is the value of temperature at point 1. Now when I look at the TS diagram, I can understand that the temperature at point 1 and the temperature at point 4 both are same. So once I know T1, I can say it is equal to T4. So T1 is equal to T4, and this will be the first answer for us. Next, now as I have written the ratio for the temperature and volume, now I can even write the ratio in the form of pressure, because we have to calculate temperatures and pressure at all points. So I'll write down, similarly T2 by T1 is equal to P2 by P1 raised to gamma minus 1 upon gamma. Now this ratio or this relation can be written for reversible adiabatic or isentropic process, that is the ratio of temperature and the ratio of pressures. Now therefore if I can say here, T2 value is given in the problem, and that is T max, which is 683 Kelvin. So 683 divided by T1. T1 we have found out just now, it is 333.55. So 333.55 is equal to, now P2 value is given in the question. P2 was 18 into 10 raised to 5. So 18 into 10 raised to 5 divided by P1 is what we have to calculate, and gamma can be taken as 1.4 for the reversible adiabatic process. So now once we have put all the values, 683 divided by 333.55, that comes out to be 2.047. Now I want P1 value here, so I'll shift this term onto the other side. So when 1.4 minus 1, which is 0.4, divide by 1.4, when it comes onto the other side, it would be reciprocal. So here I'll have 1.4, which is denominator here, will become the numerator on the left hand side, divide by 0.4, and that is equal to 18 into 10 raised to 5 divided by P1. So once I calculate this term, I'll send it into the denominator. So 18 into 10 raised to 5 will be divided by this answer, and when I calculate, I'll get P1 as 146.51 into 10 raised to 3 Newton per meter square, or if I want to convert it into bar, that will be dividing this by 10 raised to 5, and it gives me 1.465 bar. So this is the second answer, that is we have calculated the pressure at point first. So pressure and temperature are known. Next, as I have started for the process 1 to 2. Similarly, now I'll go for process 2 to 3. So I'll write down. Next is for process 2 to 3, which is reversible isothermal process. Now for that I can use the relation between the two states. For state 2 I can write down P2V2 upon T2. For state 3 P3V3 upon T3. Now since it is isothermal process, so the temperature at point 2 and point 3 they are same, and that can be understood from the TS diagram that temperature at 2 and 3 they are same, T2 is equal to T3, so we can cancel them out. Now if we see here in the problem, P2 value is known to us and we have the ratio of V3 by V2, so we can utilize that to calculate P3. So here therefore I'll keep P3 on one side, shift V3 here, so this will be P2 V2 upon V3. Now here P2 value, it is 18 into 10 raised to 5 Newton per meter square. Next, if I see in the problem, V3 by V2 is 1.5 and therefore V2 by V3 will be 1 divided by 1.5. So here I am having V2 by V3, so that will be 1 divided by 1.5. So hence the answer of P3, it comes out to be 12 into 10 raised to 5 Newton per meter square. Dividing this by 10 raised to 5, that gives me 12 bar as the third answer. Next, after finding the value at point 3, I have completed the process 2 to 3. Next is process 3 to 4. For process 3 to 4, it is reversible adiabatic, or we can say isentropic expansion process. So for that we can write the relation as P3V3 raised to gamma is equal to P4V4 raised to gamma. Now we have found out the value of P3. Next is I would be calculating the value of P4. So therefore P4 will be on one side, P3 V3 raised to gamma, V4 raised to gamma will go in the denominator, so that will be P3. Next V3 by V4 I'll take it as common and gamma will be common to both of them. Now this is the ratio of, we can say, expansion. Like during compression the ratio was V2 by V1, during expansion it will be V4 by V3 and both will be same. As I see here, V1 by V2 was 6, so we can even say that like V1 by V2, that is initial volume to final volume, or we can say bigger volume upon smaller volume. Similarly here for 3 to 4 the bigger volume is V4, so it is also equal to V4, smaller volume is V3, V4 by V3. So V1 by V2 is equal to V4 by V3. Now here we have V3 by V4, so that will be reciprocal. So therefore I'll put the values onto the next page. Now therefore P4 will be equal to P3 value. First of all, P3 is 12 into 10 raised to 5. Next, here as we see it is V3 by V4. In the data as I have written, V4 by V3 is 6. So V3 by V4 will be reciprocal, that will be 1 upon 6 raised to gamma, which is 1.4. So therefore P4 value will come out to be 0.976 into 10 raised to 5 Newton per meter square, or if I divide by 10 raised to 5, that will become 0.976 bar, and this will be the fourth answer for us. Then after we have reached at this stage, now we can say that we have found out the pressures and temperatures at all the points. I'll write them here. That is, hence the temperatures and pressures at all salient points are, now starting with the first point, that is T1. T1 is equal to 333.55 Kelvin. Next, T2 is equal to, T2 was given in the question as the maximum temperature 683 Kelvin. Next, even T3 value is same because of the isothermal process. So T2 is equal to T3. T3 is also 683 Kelvin. And T1 was equal to T4, as we can see here. Heat is rejected at constant temperature. So T1 is equal to T4, which is 333.55 Kelvin. Next, similarly, pressure at point number 1, P1, it is 1.465 bar. 1.465 bar. Next, pressure at point 2, that is the maximum pressure, and it is at point number 2, called as 18 bar, already given in the problem. Then pressure at point 3, P3 value, it is 12 bar. And at last, pressure at point number 4, that is 0.976 bar. So here we have found out all the unknowns in the first question, that is the pressure and temperatures at all salient points have been calculated. So this is the first part of the question which have been solved. So now, once I have calculated the temperatures and pressure value at all salient points, the second question was change in entropy during the isothermal expansion process. So I'll go for that. The second part in the question is calculation of change in entropy during isothermal expansion process. Now, for the change in entropy during the isothermal expansion process, it can be denoted as delta S is equal to, now for isothermal process, the isothermal expansion process is taking place from 2 to 3. So we can directly write down the formula of change in entropy, that is mR ln of final here V3 by V2, that is final volume upon initial volume. So here I have written for isothermal expansion process, V2 is the initial volume, V3 is the final volume. So it is mR ln V3 by V2, that is final volume upon initial volume. Next, here instead of mR, since we don't know the mass, here what I'll do, I'll use a small concept, that since PV, that is equal to mRT, called as the characteristic gas equation. Now mR will be equal to PV upon T, and this we have to write it for the state first, that is since the process is from 2 to 3, so I'll write down P2V2 upon T2. Instead of mR, it can be written as P2V2 upon T2, and here this will remain as it is, ln of V3 by V2. So therefore delta S will become P2 V2. Now if we see in the first part of the question, as we have found out the pressure at all salient points and even the temperatures, so P2 value is given in the problem as 18 into 10 raised to 5. Next V2 value, that is 0.18 meter cube divided by T2, and that T2 value is 683 Kelvin into ln of, now V3 by V2, see simply we have the relation V3 by V2 is equal to 1.5, that we have written in the data. So instead of V3 by V2 I can directly write it as 1.5, and into the bracket I can mention that it is given. So on calculation of this entire term, I'll get my answer of delta S as 192.34 joule per Kelvin, or I can write it as 0.192 kilojoule per Kelvin, dividing this by 1000. So this is the fifth answer for us. Now with this I have completed the second question, that is I have calculated the change in entropy during the isothermal expansion process. So I'll write down, therefore change in entropy during isothermal expansion process is equal to 0.192 kilojoule per Kelvin. After this, the last part of the problem, that is the third part, in that we have to calculate the Carnot cycle efficiency. So I'll write down calculation of Carnot cycle efficiency. Now since Carnot cycle efficiency is given by the general formula, which is maximum temperature minus minimum temperature upon maximum temperature, so therefore Carnot efficiency will be equal to, now where I have calculated all the pressures and temperatures, here if we see from the temperatures, maximum temperature is 683, so Tmax is 683 minus minimum temperature is 333.55, so 333.55 divided by the maximum temperature 683. So therefore this will give me the value of Carnot efficiency as equal to 0.5116, that is in terms of number. If I multiply it by 100, my answer will be 51.16%. And this is the sixth answer for us. And here once we have calculated the Carnot cycle efficiency, with that we can say that we have completed all the questions, and here we complete the problem.